The points 1, 9 and 4, 21 give slope 4 and intercept 5.
Welcome to Hazel Growth Hollow. If you observe the paths here, you'll see two distinct patterns. One path adds acorns at a steady, equal rate, while another holds a cache that multiplies in size. Whether the provided information appears as coordinate points on a map or as a verbal description, the mathematical objective remains the same.
We need a rule that predicts the output for any input.
The math lives inside the scenery. We observe the physical quantities and their relationships in the environment before we translate them into formal notation. By identifying what changes and what stays fixed, we can construct the specific function that records how this environment behaves. A red squirrel moves between two time-step caches. This represents a linear function passing through two specific points, 1, 9, and 4, 21.
The graph passes through 1, 9, and 4, 21. The output change is 12. The input change is 3. 12 divided by 3 is 4. 4 is the slope, the rate per input unit, not the total output change. Substituting 1, 9 gives b equals 5, so y equals 4x plus 5.
We substitute one of our known points into this equation to find the value of the y-intercept, b. Using the point 1, 9, we see that 9 equals 4 times 1 plus b. Subtracting 4 from both sides reveals that b equals 5. The resulting linear function is y equals 4x plus 5. Defining the constant difference and the starting point provides the data needed to define this linear relationship. Now we look at an exponential relationship.
From 5 to 20 in 2 steps gives a per-step factor of 2.
At x equals 0, the starting value is 5. 2 steps down the path, at x equals 2, the value has grown to 20. This growth happens over 2 distinct steps. Since the value grew from 5 to 20, the total growth factor across those 2 steps is 4. If multiplying twice yields a total factor of 4, what is the single per-step multiplying factor? Pause and consider the change. The per-step factor is 2. The starting value of 5 goes in the front of the equation, and the per-step factor of 2 becomes the exponential base. The final exponential function is y equals 5 times 2 to the power of x. Finding the per-step multiplier allows us to model this accelerating growth. Our final challenge is converting a verbal description into a formal function. Consider a savings plan that starts with $300 and gains $25 each week. Instead of standard variables, we use context-specific grammar. We'll use W to represent the number of weeks, and B of W for the total balance. We isolate the values from the description. The starting amount is 300, and the weekly linear increase is 25. The function B of W equals 300 plus 25W. This shows that descriptive words and coordinate points are simply two different ways of describing the same mathematical structure.
Sequences use positive integer inputs. In 7, 11, 15, the common difference is 4, so A of n equals 7 plus 4 times n minus 1. In 3, 6, 12, the common ratio is 2, so G of n equals 3 times 2 to the n minus 1. Here n is 1, 2, 3, and so on. Start at $300 and add $25 for each week.